Hello and welcome to our Advanced CATIA project. My name is Frank Garriga,
My name is Laurence Clarke.
and today we're going to show you how we model the oscillating cylinder steam engine. So a little bit of history. William Murdoch in 18th century created this engine. The design was very popular because it was low cost and very easily to maintain. It was mostly used on ships and other devices, mechanical devices. The engine operates with steam, so hot steam coming in to the cylinder and increases the pressure, so the piston moves forward and converts, and this piston will convert the energy into work that will move the wheel, and then cold steam will go out of the system. Now, for the team dynamic, we separated the parts by using a scale between 1 to 5, 5 being the hardest and 1 being the easiest. So each member we have his own part and will be evenly distributed by difficulty. All members will have similar scores because at the end we're gonna sum all the values of the difficult parts, and at the end we're gonna have 30 points each. The team dynamic team management. For this, we uses a Gantt chart to distribute the deadlines and to make it easiest and efficient for each member to look at the Gantt chart and notice when the task is due. This is the team dynamic management Gantt chart we use. So first we use the time sign up, we choose our partners, and then we use the part distribution following with the part design, then the drawings, then all the the sub-assembly drawings. Finally, we set up the report, the video, and revisions. The dynamic workload. So this is what each person did. Clarke was in charge of the engine assembly, the 3 sub-assemblies used for this main device, and the drawings, assembled drawings, presentation and report organization. Frank Garriga was in charge of the exploding view drawings, sub-assembly part list, material list, and all the report itself.
All right, so this is the final design of the oscillating steam cylinder. As this visual shows, the materials depend on what the part's purpose is. The bottom base is made out of wood. The flywheel, which is this portion right here, and the base frame, which is this portion right here. There's not that many stresses on them, so they can be made out of less secure or less strength. Made out of materials with less strength. As the cylinder portion shows, the higher chrome designates a harder material as there's more pressure being put into this portion of the subassembly. This drawing, or this isometric view, shows the exploded parts list of everything that is contained inside of our project. As evident, there are a lot more parts than it originally seems. This is because most of the cylinder portions, including the bolts, the O-rings, and part of the piston assemblies, which is this right here, are actually on the inside and cannot be seen from the outside looking in. As I said about the materials, the flywheel, crank disc, and crankshaft, which are the portions in the less chromed material, is a mild steel because they do not have to have as much stress as the others. Brass was used for some portions just because it had the longevity of it is quite intense, or quite long. Stainless steel was used as well as hardened aluminum for some of the materials that required to have a greater strength. Spring steel was used in the spring, as shown right here, This was the only way to make the spring, as it had to have the same requirements as a normal spring. Wood was used for the base plate, and as you can see from this portion, most of the parts were used only once. However, things such as bolts, pins, inlet-outlet pipes, and bearings were used multiple times. Now, the main assembly is divided into 4 sub-assemblies. The cylinder oscillating steam engine, like I said, was divided into 4 sub-assemblies to separate the different mechanisms. These mechanisms include the base, the cylinder, the piston, and the flywheel. Each of these sub-assemblies is constrained prior to the integration into the main assembly shown on the previous slides. Now, each sub-assembly has a specific task. We were not told which parts to put in the sub-assemblies, but we decided that the sub-assemblies that we created worked best together and should be left apart. Now, this is the first sub-assembly. This is the base. This part is important because it is the structural side of the cylinder. Without the base, the structural side of the oscillating engine. Without the base, the engine would not function as an engine, and it would not transfer the pressure and the steam into a rotational motion. Now, this is a visual of the completed assembly. Let's see. As you can see, when the piston is moved in and out, because of the steam pressure, the flywheel is rotated, and in order to keep this motion consistent, the cylinder is on a pivot and pushed in by the spring. This allows it to change angle in order to keep the piston moving in and out. Now, the base frame. This is the base frame used in the sub-assembly for the base. Whilst the part itself is not very difficult, there were some very difficult portions in its construction. The main issue we had is the creation of these 4 little holes. Now, each of these holes is not a perfect circle. They're at an angle, and they are concentric around this origin piece. Now, these were created by a construction line. Now, the construction line, which is this portion right here, was constrained to 90 degrees to a second construction line from the origin of this hole right here. Now, these lines were made this way as shown in the drawing designs from the start of the project. Once the construction lines were made, this circular portion, or this rectangular portion with fillets on the edge, was created along one, and then a symmetry tool was used to mirror first this one on this side, and then mirror both of these on the top. The second subassembly is the cylinder itself. Whilst this is the most complex portion of the report, it is also the most instrumental in the engine's ability to deliver rotational motion. As stated before, the cylinder is made out of hardened aluminum and steel. It is a much stronger material than the other parts. The reason for this is because when you remove the lagging, which is this portion up here, and you remove the cylinder, this is where the piston assembly moves in and out. Because this portion is subjected to a lot of stress, 8 bolts were used in total. These holes are threaded, and they fit these bolts right here. When the rear portion, which is this, and the front portion are put into place and the bolts inserted into each of these holes, the cylinder assembly becomes very strong and able to withstand the pressure exerted by the pistons. This final assembly, or sorry, this third assembly, whilst it looks the most simple, it actually presented us with quite a few issues. In the original design drawings, this portion right here, which is the actual piston head, was one part. However, it's actually multiple materials. Now, CATIA will not let you make one part out of multiple materials, so we were forced to create a second assembly inside of this piston assembly. Now, this piston assembly is made with a rod that is threaded inside a connection portion. This is called the piston rod big end, and on the other side is the second assembly. Now, this black ring around the middle is actually an O-ring. Now, the O-ring was positioned inside of this piston head through the use of a groove tool. Now, the piston head has this groove that goes around the entire outside, and the O-ring was created by using a profile curve and a guide curve. Now, the guide curve is the circle, and the profile curve is this little circle on the inside. Once these two parts were made and materials assigned to both, with the O-ring consisting of rubber and the piston head consisting of metal, or of steel, I believe, the parts, or the assembly, was ready to be added into the second main assembly. This O-ring is there because it makes a flush fit with the inside of the cylinder, allowing it to be as efficient as possible for the steam it produces.
Now, for the subassembly of the flywheel, this will be the last subassembly. This is one of the most important parts, because after the piston do his work, it goes and moves this wheel, and this wheel is connected to other devices that will be moved as well. So for the flywheel itself, this part wasn't that difficult to create, but the main difficulty on this one was the circular holes on the middle of the part. This hole was created by using one hole and then use the circular pattern tool, and this pattern was used 6 intents of equal distance between the circular surface, right? So here I use the crown definition to successfully do the holes inside the wheel.
Once all of these assemblies were built separately, they were all uploaded into the same master assembly, which was what was shown earlier in this report. In conclusion, each part was perfectly measured to minimize the dimension mismatch. This was accomplished through careful communication between both team members. However, not all of the parts made were fully dimensioned for us in the beginning. Assumptions were made for any dimension not specified in the parts drawing provided by Professor Gribbons. Most of these assumptions were done for the missing dimension fillets. In order to do this correctly, one team member chose an initial fillet of 1 millimeter, and the other team member decided to follow that, and all the subsequent parts contained this same fillet. Assumptions were also made concerning the construction of the nuts and bolts, which did not appear on the dimension diagrams provided. These nuts and bolts were not taken out of a catalog, but rather created using threads used inside of the assembled pieces and parts. Thank you for taking the time to watch this report. We hope you found some of it enjoyable.